Hello, everyone. Welcome to our first technical session in the summer 2022 cohort brought to you by Hamoye. As most of you already know, Hamoye is an edtech startup with a mission to prepare young professionals and college students for their choice careers in data and the future of work. We do that via our internship programs, which simulate the conditions you will face while working in a real work environment. Our internships will expose you to specially designed courses, industry-relevant capstone projects, and career coaching webinars with industry experts like what we are having right now. My name is Basil Ihoma, and I am a data engineer at Moye Air Labs. And I'm joining you from Lagos, Nigeria, and I'll be your host for today's session. I would like to welcome to the session everyone present, our incredible interns in this Hamoye cohort. Kudos to you for making it this far. Thanks to the Hamoye Fellows and the Hamoye team who have made this session possible. For today's session, we have a rather interesting topic: leveraging Kubernetes for platform agnostic ML deployment. There is no against stating the fact that when it comes to large-scale data processing and machine learning, Apache Spark is no doubt one of the top-tier battle-tested frameworks out there for handling batch or streaming workloads. The ease of use, built-in machine learning models, and multi-language support makes it a very attractive choice for data ones. Also, bootstrapping and getting off the ground could be difficult for most teams without leveraging a Spark cluster that is already pre-provisioned and provided as a managed service in the cloud. Why this is a very attractive choice to get going in the long run, it could be a very expensive option if not well managed. However, running machine learning workloads on pipelines as containerized Docker packages on Kubernetes provides an industry agnostic abstraction layer, and as a result, it improves operational efficiency and reduces overall compute costs. Most importantly, you can easily target your Spark workload deployment to run on any major cloud or on-prem infrastructure. For this session, we have an industry expert by name Mr. Charles Adetiloye, the co-founder of MavenCode. Mr. Charles has over 15 years worth of experience consulting and implementing large-scale data processing, AI, and machine learning software platforms across different industry verticals. He has previously worked with Lightbend, Twitter, but to name a few. He is the CEO and co-founder of one of the most successful providers of consulting services and builders of large-scale distributed reactive backend systems, MavenCode. Charles has over a decade worth of experience in machine learning operations. We'll be sharing his thoughts and experience on how to make it easy for us to run in production deployment of our machine learning workloads and pipelines on Kubernetes, which seamlessly allows us to port our implementation from a local Kubernetes setup
Just before we hand over to Mr. Charles, I'd like us to take note of the following housekeeping rules. A form is going to be dropped. A form for attendance will be dropped for us. And the secret code to use is deployment, all lowercase. The form will be opened for only 10 minutes, starting now. We have pinned the first attendance form link on YouTube, Zoom, and Slack. We want you to fill your form quickly in order to focus on the presentation. We also like to point out that you should feel free to ask your questions, post your questions in the YouTube chat box, as well as the Zoom chat box session. You can also use our slido.com site with the event code 7833995. So you go on slide.do and you use the event code 7833995. At this point, we would like to welcome Mr. Charles Adetiloye to take over the presentation. Hello, Mr. Charles.
Yeah, thank you. Can you hear me now? I think.
Yes, we can hear you.
Okay, all right, cool. It's good to see everyone this morning, this afternoon, this evening, wherever you are. So we're going to be talking about cloud agnostic ML workload deployment. This was actually a talk that we gave at a conference in Austin a few weeks ago. So I'll go through what we talked about, and at the end of it, I'll leave some time for questions and answers. So I'm going to share my screen real quick, and let me know when you can see it. All right. So we're going to be talking about how you implement cloud agnostic machine learning workflow on Kubernetes. And in this use case, we're going to talk about Apache Beam, which is a data processing pipeline that basically allows you to build a unified data processing framework for your batch and streaming workflow. We gave this presentation about a month ago at the Beam Summit in Austin, my colleague and I, Alex Lammer. A little bit about me. I'm the co-founder and one of the lead ML engineers at MavenCode. I've been doing this for a while now, so a little bit. I've had some battle scars building MLOps platform for companies and presenting some of the work that we've done in this space. MavenCode is an AI solutions company. We're based in Dallas. We do a lot of things around ML ops, and we basically consult in this space. We build products and machine learning pipelines to basically help our customers put their models in production and scale it out. So the agenda for today, we're going to make a case for why you need a cloud agnostic ML deployment. You can, if you're doing a lot of things around ML and you're building ML workflows, you can decide to build it in the cloud on any of the managed services, but we're taking this a notch further and we're making a case for the reason why you might want to stay cloud agnostic. Then we'll talk about building it all on Kubernetes, basically leveraging Kubernetes as kind of like your cloud OS that allows you to like build applications that you can deploy across the major cloud providers or on-prem. And we'll talk a little bit about the Beam jobs and how you can use Argo workflow, which is a workflow orchestration engine to deploy your ML workflows and things like that. Then we'll talk a little bit about how to build an agile team approach so that if you're working in a team, how you can collaborate with your team members and build all these workflows and deploy it and things like that. In the end, we'll conclude by the lessons learned, what we've learned working in this space, and how you can learn from some of the things we've learned in the process of building all these things. So making the case for cloud agnostic ML workflow deployment. So if you look at it, basically machine learning is basically around building statistical models that can from curated data, and you can basically use that to build prediction. That's what ML is all about, if you want to distill it. So you can say it's mainly statistics. And the main artifacts, whenever you're doing any ML projects at the data sets, you can't do any ML project without data. You build an ML model and you build your code. These three things will change over the lifetime of your model or the algorithm that you're building for ML. You're going to get more data as more people use your application. You're going to have to retrain your model. And over time, you may need to improve your code as well. So to put it in a simple way, this is how ML workflow looks like. You acquire data from IoT devices, database, unstructured file systems. But this data are still in a raw state, so you can't just plug it into a model and start making predictions. You need to curate the data sets. That means you do feature engineering, you select what you need. You visualize the data. If you're working in a big company, you probably have like an analyst, a data analyst, business analyst, and they basically visualize the data. You do principal component analysis to see what matters and what doesn't really matter. After that, you basically extract the things you need and you train a model. And the first time you train your model, it may not be accurate. So you basically do a lot of tuning, like vary the hyperparameters that basically affect the model performance. And you tune the models, you run through multiple iterations until you think you got what you need. And once you have what you need, you can now package the model and deploy the model in production. So then once you deploy the model in production, you start monitoring it to make sure things are coming out as expected. You don't want any false positives. So if, let's say you're building a model for a self-driving car like Tesla that basically identifies objects on the road, you want to make sure the model is not making any false positive or false negative. So if there's a pedestrian, you don't want to say it's something else, or if there's something else, you don't want to say it's a pedestrian. So depending on the kind of model you're building, you need to make sure your model is good enough and you're tracking the model so that you can know, like, if this model is behaving in a way that is not in line with what you expect, you can always retrain the model. So you monitor the model. And there's a concept around this called model explainability. So if a model makes a prediction, you want to be able to like explain the predictions of the model based on all the input variables that went into the prediction. So you want to be able to do that as well. So if you're in the ML space and you're building MLs, and like most of you have done, you'll probably run through a similar pattern to this iteration, and that's what we do. So the challenges in doing this is basically if you build that workflow, like any software engineering team, you want to make sure that you're building something that can be reused and you can easily scale. And if you're not able to scale it, then there's no reason implementing a software for it. So the challenges in ML workflows right now is reproducibility. If you build your models in your Jupyter notebook, how can you make it reproducible? That means I want to basically make it into a product that I can instantiate multiple times and scale out. So can you make it reproducible? In addition to that, you want to make sure it's reusable. What I mean by reusable is like the success in software engineering in the past few decades has been around the concept of object-oriented programming, where you build APIs and you consume the API and you utilize all these APIs without knowing what's behind the scene. So bringing this same knowledge and way of thinking to ML operations includes you building components that you can share with your team, and your team members can basically reuse it rather than trying to like create everything from scratch. So if you have a data connector component, I should be able to grab that component, reuse it, and do all the things I need to do around it without trying to go build my data sourcing component and things like that. After that, you need to be able to manage it. So manageability is one of the important facets of training a model, because over time, as you get more data, you train your model, and you want to make sure you're tracking the model you're building, versioning it correctly. So making sure you have a system in place that allows you to manage all your model artifacts is very important. Then the next thing now is the automation, where after you've done all these things, you want to be able to automate the process so that you can have things like a CI/CD system you have in traditional software, and the same principle apply to what you're doing in ML engineering and stuff like that. So these are the challenges in this space, and it's still evolving. It's not yet fully defined. And the goal is to get to a state where we can automate a lot of all these things so that you can focus on the ad problems and not worry about the underlying resource constraints or the challenges in building ML. So that's why a lot of ML projects, they're not really very successful now, because it takes a lot of work to bootstrap all the things you need to do and all the infrastructures you need to put in place. So the reality is like things get more complex as you build all these things. You have different data sources. I think most of the stuff you guys have done right now involves you basically getting the curated data on Argo and stuff like that. But over time, you find it difficult. Like if you want to build anything in the big enterprise, once you start working in big companies, or if you're there already, you need to worry about where the data is coming from. The database, it might be spread all over. You have different files of Excel and data that you want to pick. You have your story buckets that contains different data. Some of this data may be streaming data if you're doing things with IoT, or you have a third party supplying you the data. So you deal with all this complexity whenever you're trying to build any ML project. And this data is siloed across different parts of the organization. And you can't just have access to all the holistic data that you need to run your models. Then the other thing, again, is like some data are guided by some privacy requirements. So like if I'm building an ML application right now that requires healthcare data, there's some things that I'm not going to be privileged to have access to, because you need to protect the identity of the patient and stuff like that. There's something called GDPR right now, which is the kind of restriction in the EU that basically mandates some certain constraints and requirements about customer data and data that companies deal with and stuff like that. So you deal with all those things whenever you build an ML, and you need to have a way of working your way through it. And the other thing is the data availability. We always think that we'll have the data that we need right away, but in some cases, the data is time bounded. Time bounded in the sense that some of this data could be streaming, could be batched, could be delivered hourly, daily, or monthly. You're not going to get access to it until the time constraints around it is met. So some data are basically time bounded. So all these things makes it complex for you to build a production ready enterprise application. So just to like blow out the picture a little bit more from what we saw earlier. So this is like kind of the workflow where you have the data coming in from all these different sources. And you have different key players in this process. You have like all your data engineers and business analysts, domain expert, basically exploring the data, wrangling the data. They refine the data. So, and you have a data lake where all this data is coming in, you're processing it, and you're analyzing it. You're just trying to understand what you need. And you're basically writing it to a data lake where You have a continuous inflow of data organized by time. And so every time you receive the data, you process it, you put it in the data lake, you still maintain a reference to your raw data in case you need to go do some more processing or wrangling, stuff like that. Then the other thing after that is like, even the refined data might not be, it's not in the form that your data scientists need, they still need to derive some things around it. So one of the things we do right now is to create a feature store that contains the features that you need in your model. So you have a feature schema that defines all the attributes and everything that you have in your model, you need in your model. So we can create a schema that basically represents the feature vectors and group them to get in different, create groups for them. So each data scientist on the team can now grab the features they need, train their model on it, and once they think the model is good enough, they can promote the model to production, and the model can now be managed, and you can run it through several iterations. You can basically monitor the model to make sure the model is in a good shape. So this is a high-level overview of how things are organized and grouped whenever you're working collaboratively in the team, where you get your raw data, you purify it into the data lake, you refine it, then you create all these feature sets that the data scientists can now grab and use for their model training. Then you have a process of orchestrating the model into production. So our approach to ML deployment in our team is basically involves, because we have a polyglot team. Polyglot in the sense that people write things in different languages. You have people that are comfortable with Scala, Golang, Java, and Python. So we try to like encourage people to do what they use what they can, they know how to use in the best way. So in this case, you try to use the best tool to solve the problems. You don't try to like rewrite a Java code in Python or rewrite a Python code in Java just because that's your preference. So, but what we do is to basically containerize all these things into a Docker container. And basically we create all these codes. In this case, we use Apache Beam a lot. So we containerize this code and everything runs in a Docker container. And Beam, one of the advantages of Apache Beam is the runtime portability. So it makes it easy for us to basically run it on different frameworks. You can run your Beam job on Dataflow. If you're on Google Cloud, you can run it on Spark, you can run it on Splink cluster. So we basically leverage that portability and things like that. Then the other thing I talked about reusability earlier is like we componentize our code into unit of works. So we can have different data source component that connects to database, that connects to file system, or that connects to like streaming data source like Kafka. And you have the data writer component too that writes out the data in the way that we want it. Then we have the feature store component that basically helps us load up a schema and apply the transform data to the schema so that you can now output the data in the structure that the data scientists will need based on the schema definition. Then we have the model training components, which basically leverage on Kubeflow operators that allows us to basically build all these components that makes it easy for us to like train models and stuff like that. Then we have the model serving component that allows us to take the trained model, we'll wrap it up, and we'll deploy it, and that model can now be used for inferencing and things like that. And basically we have a monitoring capability on that model serving component that allows us to monitor the traffic inflow and outflow from the model. Then we version all these containers and we deploy them with Argo. So Argo is an orchestration tool. I'm going to talk about it later on that allows us to like package all these applications and deploy them as a workflow. So basically a workflow is basically different containers that you basically tie together and you enforce some certain dependencies between the containers so that if container 1 runs to complete, container 2 starts, container 3 starts, and if anything fails, everything fails. So you basically can create a workflow. So with this, we're basically able to like improve our team operational efficiency and consistency. And we can easily basically deploy all the things that we're doing on Kubernetes. And it's easy for us to gain portability across all the major cloud providers. So we're not tied to a particular technology stack. We can take the same code that we wrote and deploy it on any of the major cloud providers or deploy them on-prem. So basically, I'll talk a little bit about Apache Beam. Basically, with this approach, we're using Beam, and Beam is an SDK that allows you to write codes basically with the SDK, and you can write a Beam code in Java, Python, and Go. And basically, the code can now be deployed using what's called the Runner API on any of the major cloud runners. So you can think about the cloud runners and like you have a Spark cluster, or you have a Flink cluster, or you have Direct Runner, which is for your local, or you have a Dataflow runner, which is more tied to Google Cloud. So the whole idea with Apache Beam is like you can write all these codes, and you use a portability API to like write it through the Runner API, and you deploy it on any of the runners. So that means if you're a data scientist and you're good with Python, you can use Beam Python code. If you're a data engineer and you're good with Java, you can do Beam Java. And if you're still like a Go developer and you want to write your code in Go because it does the job well, you can write it in Beam Go SDK, and everything ports directly to the pipeline API below. And the pipeline API basically contains a translator that can allow you to target any of the runners out there. So the advantage is like it's a unified pipeline. So if you're running a code for processing streaming jobs and batch jobs, they're basically the same logic. I mean, basically, it's the APIs is all unified. You treat everything as a P collection. They call it P collection, and you can now process it. So streaming data is just a continuous infinite table, whereas your batch data, you have a defined endpoint. So you have a unified pipeline for that. So obviously we have the multi-language support. So the Beam API targets different SDK, and you have multiple runner support. So the runners are kind of like your cluster, like I said earlier. And the cool thing about this is like, for those of you that have worked with TensorFlow, you've probably seen TFX. And for those of you you've worked with Pandas, Beam supports data frame. It's a new concept around it, and Beam ML and Beam SQL. So all those things makes it easy, and that's why Apache Beam is really interesting, and it's one of the things that you need to look into going forward. So to expand that a little bit, the whole idea of this is to basically write a code that is portable across infrastructure. So what I mean by that is like you have portability on the application side where we can write things in any of these SDKs and we can deploy it on any of these runners. So, but again, we want to leverage this beyond just Apache Beam that gives the developer the flexibility. We want to be able to deploy this on any infrastructure, on-prem, if you have a bunch of server in-house, or on AWS, or on Azure, or on Google Cloud. And for us to do that, one thing that we can leverage on is Kubernetes. Kubernetes is kind of like the industry standard now, where you have the specs that defines how you deploy application, how you scale it out, and and a lot of all these cloud providers, they support Kubernetes. They basically all support Kubernetes because they have managed services for running Kubernetes. You have JKE on Google Cloud, you have AKS on Azure, you have EKS on Amazon, and you can set up your own Kubernetes cluster as well. So once you have Kubernetes running, you can just create the descriptors that allows you to deploy the application. So the goal for building a platform agnostic ML practice is for you to build all these things on top of Kubernetes, so that as long as you have Kubernetes running on any of those infrastructure, you can easily shift and lift your ML projects and deploy them on those platforms. So the advantages of running Apache Beam ML on Kubernetes is like we can leverage the Beam portability multi-language semantics, basically supporting different languages, Python, Java, Scala, and I think TypeScript and Golang. And you can use something called extended transforms. So you can basically call a Java API from inside Python. It makes it easy. You have rich libraries of API that can handle different workflow processes. You guys should look at TFX, which is called TensorFlow Extended, Beam SQL, and Connector IOs. So there are a bunch of rich toolings that allows you to do a lot of things very easily. And the Beam job can be containerized as unit of work, and it can be easily maintained on its own and deployed across the Kubernetes cluster. So that means if you're writing your application, we containerize it as a Docker. That Docker gets wrapped up as a pod, and we deploy it on Kubernetes. And the infrastructure portability, like I said earlier, we want to make it easy for you to like migrate your workload across cloud infrastructure. And you can even run it on your local. So once you set up Kubernetes on your local, you can create the same environment. And once you think your application is ready for deployment, you can push it to the cloud infrastructure. So, and one of the great advantage of this is like you can create a consistent operating environment for your data scientists, ML engineers, and data engineers, so that the challenges in building all these things stems from the fact that people are using different tools. You may see your data scientists using Jupyter Notebook, the data engineers using VS Code, someone else is using PyCharm or IntelliJ. So you want to create this consistent environment that makes it easy for everyone to work from the same base in a mono repo, and they can easily pull whatever they want to do and deploy it and stuff like that. Then it's easy for debugging and testing on local environments, so that a lot of the times when you're using all this cloud infrastructure, you're deploying these applications in the cloud and you don't have enough insights into what's going on, and you need to check the logs and stuff like that. So, but what if you can basically debug all these things locally and test that everything is okay before you shift and move it to the cloud and things like that? So that's it about cloud agnostic infrastructure deployment, and I hope I've a good case for things like we'll look at how we'll build it all on Kubernetes a little bit more deeper. This is the stack I showed you earlier, where you have the Beam job and on the code side, we have the portability. We want to give you flexibility to run either Java, Scala, Python, Go, or SQL. And on the infrastructure side, on the runner side, we want to make sure that you can deploy your code on any of the clusters available, as long as they're running on Kubernetes. Then on the infrastructure side, we give you portability across compute resource. That's your local dev, your on-prem, or your on-cloud infrastructure. So I'll talk a little bit about the portability architecture. It might be a little bit over the top, but I'll try to go through it. The whole idea around Beam Portability, which is a project heavily supported at Google. Google has a product that they run, data flow. If basically you should be able to write your pipeline code in any of the major languages. Okay, can people see my screen? Let me know. I'm getting a notification there. Some people cannot.
Yes, we can see your screen.
Okay, thank you. So, so the whole idea behind this is like you have this portability in Beam that allows you to write codes in different Beam SDK, and you can basically target different execution environment, different clusters. So just to keep it simple. So the way this works is like Beam has SDKs for Java, for Python, for Golang, and they have a spec so that in future they can support any other language like Rust, Haskell, and they're working on TypeScript right now, so that you can write TypeScript, JavaScript kind of language that runs on Go. And you have the Run API that basically inspects this, because all these things are built on specs. The Run API inspects all these things and basically understands what the SDK is trying to say, and it converts it to proto formats. And that proto format can now be targeted to any runner that you specified, Spark runner or Flink runner or any other runners, as long as the spec has been implemented. And that runner basically has a Beam model for executing the code in different environments, which could be Java, Python, Golang, and stuff like that. So that means you can write a Beam job in Java, and it gets converted to a format that can be deployed on Spark cluster. So it's kind of like an idiomatic way of expressing your pipeline code, and you can now take that expression, port it, and have it run on all these different runner specifications. So they have a whole spec around that you can look into. It's evolving. So the goal is to make it easy for you to write your pipeline codes and your DAGs and everything like that. So just to like explain it a little bit more. So this is a simple Beam job, kind of like it's in Python. So If you want to deploy the job, in this case, I'm using the portable runner. So they have different runners. They have direct runner. The portable runner is the new version that allows you to like target all these different environments. So I will basically specify all the things I want to do. Then I will start my job. I'll specify the runner type and the job endpoint and the environment type. And I will now kick off my job. This is the application entry point. So the job endpoint is kind of like is a service endpoint. So what this is saying is like, I'm running this job. I want you to submit it to this service endpoint, and this service endpoint is going to deploy to my cluster. So the job service endpoint basically wraps up all the complex things you saw in the previous slide into a Docker container. They publish it and it's publicly available. And I can decide to specify the kind of cluster where the job is going to run. In this case, once I run my code, my pipeline codes, I'll target to the Spark cluster. I'll specify I'll start the Beam Spark job server, and I'll specify the cluster I want it to run on. That same code, that's the beauty of this. I can tell it to run on a Flink cluster. I'll take this Docker container, and I'll basically submit my job to the Flink endpoint without changing anything. As long as Flink runners implement all the spec, and as long as the Spark job server implements all the spec, the job is going to run completely and it's going to be deployed on the right cluster. So once I take that code, I can deploy it on the Spark cluster, I can deploy on my Flink cluster, and I can keep on extending this to all the supported runners. As long as they're supported and there's an implementation for this job service endpoint, I can take my job, run it, submit it to the endpoint, and it will deploy to the right cluster. So this is my Spark master pointing to the Spark cluster, and this is the Flink master URL pointing to the Flink master URL. And so that way, I can target different runners. And this could be Java code. This is a Python instance. It could be a Java code. It could be a TypeScript code or a Golang code. I'll submit it to these endpoints, and from there, I'll submit the job gets posted to my cluster. And the beauty of this is like everything, I can have my cluster running on my local host, on my laptop, in a Minikube, on a full-fledged Kubernetes cluster. So we have this portability across infrastructure, the portability of runners, and the portability of the code. So the advantages of this portability is basically a rich set of IOs. So a lot of the times when you're writing ML code, you spend your time reading data and writing data out. So the Beam project has a lot of rich IOs for like all the major data sources, Kafka, PubSub, Kinesis, you name it. So we can easily leverage on all the myriads of APIs that already exist and use them. They have this service, this something called the expansion service that allows you to call APIs from outside the particular SDK you're using. In this case, you can call it Java functionality from Python, or you can call it Python functionality from Java. So it basically allows you to expand the functionality of the APIs beyond what is presently in that SDK implementation. So that's one of the big advantages of this. So the infrastructure portability on Kubernetes with Apache Spark. So let's zoom in on Apache Spark use case. So let's imagine this is you're the data scientist, you're writing your code. While you're still developing, you build your Beam job. You submit it to the job service, and you have a Spark cluster running on your local. So that means you have your Spark master and all the worker nodes. So once you're done with your job and everything is good, you post it. You send it to the job service. The job service will say that, okay, this job needs to be submitted to this Spark cluster, and you post everything there, and it's all running on Minikube. The beauty of this is like you can easily and quickly see what's going on. You can subsample your data sets, test it out on the local, make sure everything is okay. If everything is okay, then you can now take that code and deploy it on the production infrastructure. So the cool thing about this is like you have almost the same replica of whatever you deployed on your local infrastructure, in this case, your laptop. You have almost the same thing on the production environment. So there's 0 to nothing impedance mismatch between what the characteristic of your code on your local and in the production infrastructure. So you run your Beam code, you package it up, same code, and you can turn around and deploy it on the production infrastructure. Same way, you have the job service, you have the Spark master, the workers, and everything, and you deploy it on all the cloud infrastructure. So in this case, you can now have a bigger resource pool where you can deploy things and run it in large scale. So pipeline package management and deployment on Kubernetes, we use Customize, which basically allows you to like package all this infrastructure and deploy them easily so that you can basically, one of the big things that you see whenever you're building application for Kubernetes is like you deal with a lot of YAML files, and it could become a bit of a pain because yeah, managing deployment descriptors is a little bit painful. So we use and leverage Customize for this. So we deploy the entire cluster with Customize. It allows you to define the base YAML, and you can keep extending it. You can version control it, and we can use GitOps, basically managing the whole infrastructure through Git. So whenever there's a new version of a Spark or a Flink, we don't have to worry about like, oh, how do we deploy all these things? We can just go in and bump up a version and basically reapply the configuration to the cluster, and all the underlying components that we need to run on the cluster will basically get bumped up, and they can now and they have a flag that you used to like deploy to dev, deploy different infrastructure, a company where you have multi-cloud and hybrid cloud strategy, and you don't want to just put your eggs in one basket, you can basically leverage that. So it's easy for us to extend what we're doing. We can progressively extend and manage various versions of the package. And as the code base increases and you add more work, we add more stuff to your body of work, you can easily see how things are going and extend what's going on. So just to like make that a little bit more visual and add into the diagram we saw earlier. So this is the developer working on their Beam code, and we have a Git repository where we target and build all this manifest. So we have the Spark manifest that we use to deploy the Spark cluster on your local and in the production environment. Remember, we want to maintain parity between the environments and make sure there's no difference between what runs on your local and what runs on-prem. So that way you can shift and leave the same code between your local and any other infrastructure that you're using. So every developer will come and basically they'll do a Git pull, run the manifest against the cluster, and the developers, the data scientists, ML engineers can basically run off the same code base for the components that they're using. It's not like somebody's running a call for this version and the other person is running a Maven install for this version. So we try to maintain that consistency across all what all our engineers are working on. And same manifesting scripts, same version, you can apply to the cloud infrastructure that you have. And stuff like that. So I think I have a quick demo that I can show to like walk you through how this fits together. Are we doing on time? Okay, so this is a quick demo. Basically, this is our code layout where we have a makefile that runs everything. And the makefile basically deploys everything that we need to deploy. This is a Kubernetes cluster running on my local. I'll do make local deploy. So basically what I'm doing is like, I'm doing a make local deploy. Let me see. So the make local deploy basically does a scaffold. We use a tool called scaffold that basically builds all the containers that we need. So in this case, we need a Spark container to run the Spark jobs. Then we need a manifest to install. The manifest basically is what the customer is install. And this is a manifest file. So we basically build and package the manifest file. Right here, we have the Spark manifest for the master node, the worker node, and everything that we need to do about them. So once we have the manifest, we'll apply it to the cluster. And that's what we did right here. Then we run the Beam, the portability, we run the Beam job server, the Spark master, and the Spark worker nodes. We deploy them through the manifest. So that's what the manifest does right here, the Beam job service, the Spark cluster. So we're building the Spark cluster and we're building the job service endpoint. So remember, we saw the job service endpoint and the Spark master. So once we do that, we have the job service running. Let me see that. Bam, bam, bam. So we're just looking at the pods to the job service pod. So that means we tell into the container to see the logs and see how everything is going. Then the other thing that we check is to see if the Spark master is running. So basically we're going to write our code, and our code will submit our job to the job service, and the job service will submit the job to the Spark cluster that is running on my to the job service, and it's going to deploy it on the Spark cluster. And everything is running on Kubernetes on my local. Two worker nodes. We're running on my local, so we don't want to blow it up. So we have 2 Docker containers as workers, and we have 1 Docker container as a master. So what we now do is we take our Python Beam job, and we now submit it to the job service. So basically, we've posted and submitted the job to the job service. So the job basically gets submitted to the job service. The job service will take it and submit it to this cluster. So if you go back and refresh that page, you now see the application running. We've submitted a Beam job, Beam pipeline job written in Python to a Spark cluster through the job service endpoint, and everything running on Kubernetes. Thing. We went just we have the code layer is a bit one-time environment, Spark, Link, and Dataflow, or whatever environment you decide to run on. And we leverage existing functionalities in the Beam API, especially the Beam Java, which that was the first SDK that wrote. So it's easier to grab a lot of all the IO stuff you need. And we use Customize to manage the deployment on either of us or on either Spark or Link clusters on the Kubernetes. So orchestration of Beam jobs with Argo, that's the next thing we're going to talk about. So you've built all these jobs, but in reality, it's every job you write is a multi-stage process. You process data, you process the data, you prepare data, you spin it up for model training and stuff like that. So you want to see the big picture, and the way you do that is leverage Argo workflow. It allows you to construct your workflows and things like that. So we've achieved portability of code and portability of infrastructure, but beyond that, we need to create workflows that can chain all these tasks together that we need to execute together while also enforcing the dependencies between them. So with that, then what we have on Beam with Argo. So Argo workflow is a container native workflow engine. What that means is it only supports Docker, and you can only run it on Kubernetes. And for orchestrating parallel jobs on Kubernetes, so everything runs on Kubernetes. You create a workflow and you kick off the workflow, and everything runs on Kubernetes. So Why use Argo with Beam? It runs natively on Kubernetes. Again, we want to run all our resource on Kubernetes because we want to be able to deploy on Kubernetes. We can define each stage of the Beam job task that runs in its own container. So we can containerize each stage of our workflow. The data processing stage, the feature selection stage, the model training, the inferencing stage, everything can be containerized. And the Argo workflow abstraction makes it easy for us to create all these multi-step tasks with varying availability and latencies. And it's easy to compose complex tasks as a series of steps. So one mistake that people do is like you try to build everything in one, like Jupyter notebook. And whenever you change something somewhere, it's going to throw off your entire code. So one of the things we do is to like chunk this up into small steps that can be containerized, and we create this workflow, and that workflow gets deployed on the infrastructure for us. So we'll take a simple example of this. Let's look at this simple workflow where you have streaming job coming in, and you have a Kafka reader. We do enrichment. So imagine this is your raw data coming from your IoT device. Let's say you have a sensor and it's sending data, and all those data the Kafka reader components that all the message from the queue. We do feature enrichment, which is like we enrich the data that you get from the reader. So let's say you're tracking the application. Part of the feature enrichment will be like if you get a latitude and longitude, you want to basically convert it to physical address. And so like it's in a meaningful form and you have a structure to it and stuff like that, or vice versa. So we get all this data coming in, then we have a component that will split it up into training and testing data sets. That means as the data comes in, it will basically bunch it up, write it into a location, then randomly shuffle it, then split it into your training testing split ratio, which will be 70, 30, 60, 40, whatever you decide to use. So the cool thing about this is like you can have different ML engineers or different people on your team responsible for each component, somebody responsible for the Kafka component, somebody responsible for the components that you need, which is your feature engineer components that basically contains all the things you need. And there's somebody else responsible for the ML training, and they're going to just grab the data split component that someone else has written and basically use it to like train and run your model and stuff like that. And you can now connect everything together through Argo DSL, which basically chains everything together. And you can treat each component as a black box, and you're only responsible for the IO and everything that comes in and goes out between the components. So, so this is this is kind of like a DAG. The Argo workflow DAG is basically, it never turns back. So it's called the direct acyclic graph. You have this component gets an output, it goes to the next component, but the next component is not going to go back and talk to this guy. So it's always flowing forward. So you can think about it as a stream. They say water never flows backward, it only flows in one direction. If it flows backward, then something is wrong. So you have all these components basically generating output, and the output of this goes into this. The output of this goes into other components, and you can have a component feed two or more component. It doesn't really matter. You can have more component, but you can never have the graph turn back. So this is the DAG, and this is a workflow definition. So there's a spec for defining the workflow and everything you need. So in this case, you have the workflow, the Beam DAG, and all the things that we want to run. We have the Kafka reader, we have the enrichment transform components, we have the data split components, and we basically create all the dependencies. But this is how you define the YAML file to deploy this on Kubernetes. So whenever you deploy this on Argo, you're going to see something like this, which is similar to what we have here. This is a pictorial representation. And this is how it looks on the Argo workflow, where you create a Beam DAG. You have a Kafka reader, the enrichment, the data split, and the model training and testing components that can happen in parallel, and everything runs in Kubernetes. So I think there's another demo right here. So I'm just going to run this real quick. So this is a workflow DAG. This is how it looks. You have all these components. Like I said, each one is a Docker container. You have this Docker container, you have this container, you have all these things that are containerized. So this is a workflow DAG representation. So we can now take that, we'll basically run a makefile, and the makefile basically deploys a DAG. So it deploys a DAG onto the cluster. So we'll go in and look at the Argo dashboard. So they have a fancy UI that allows you to see what's going on. We basically copied the diagram we saw earlier from there. So what this is doing is like it's going out, grabbing my Docker container that contains my Kafka reader components and using it to run the Kafka component. Once the Kafka component runs and start pulling data, it's going to push the data to the enrichment component, and the enrichment component is going to run. I think we fast forwarded this video to make sure it was, I think it runs for a lot much longer. Then it's going to read up the data sets and enrich it. Then the next thing is a data splitter component. It's going to basically grab the data from that came in and it's been enriched, and it's going to basically randomly shuffle it and split it in a 70-30 or 60-30 ratio. So we have a definition for that as well. And once it does that, then it splits it out into training and the testing components. So it fits in the data to this component. So this component will basically train, and this component will basically test. The train basically tests the results of the training and stuff like that. So that's how everything works. So against like whenever you're running this pipeline. So it takes a little while to run to complete, but I can just move on. So the question now is like, how do you get these workflows to kick off? So there's something called the Argo events that basically listens to all these events, because everything in life is event driven. Something happens, then the other things kick off. So so we have Argo events for doing that. So the Argo event basically listens to like all these major events and triggers a workflow. So there's an Argo event listener for like Git commit, so that whenever your code changes and you push it to Git, it will trigger a workflow. There's an Argo event for file drop on S3 bucket or Google Storage bucket, and whenever that event occurs, it triggers a workflow. So there are different Argo events. There's a calendar Argo event that listens for a calendar date change, and it triggers a workflow. So it basically allows you to like monitor all these events and trigger the workflows for the events. And you can have a cron-based event trigger as well. That means you want this event to fire every 3 months or every month or every week or every hour. So you can have that and stuff like that. The other thing about this is like you can have conditionals as part of your trigger. Like if these two things happen, then trigger my workflow. So what that means is like, if let's say you're expecting a data from 2 sources, so I can say don't start the model training workflow until data from source 1 and source 2 has been delivered. Once the data has been delivered, trigger the workflow and run the operation to complete. So you can have that. And the cool thing about being cloud agnostic and running things with Argo is like you're not tied to any managed services. So all these things, you might be able to do 1 or 2 of it by running on Amazon or Google Cloud or Azure, where you're leveraging the managed services, but you lose the portability. What that means is like you're forever tied to that infrastructure. So the Argo approach allows us to create workflows on all these different cloud infrastructures without getting completely tied up to them. And the other thing is like everything is native to Kubernetes. So with that, we can easily do shift and lift, and it's all portable across the infrastructure that we're running on. So I think we have another demo around the Argo event. So this is basically a calendar scheduler that will trigger the workflow based on events on the calendar. So basically, we want to schedule the job to trigger every hour. So each hour, it triggers and runs events, and it kicks off the workflow. So again, you define the YAML for that. They have a fancy UI. Once you deploy the events YAML, you can view it on the UI. So you guys can check out the Argo project. It's a big project right now. So whenever you have an event, you create an event spec, that means you want to trigger this event every hour and 30 minutes past the hour. So, and you have the workflow that you want to trigger. Which is a DAG you have right there. So that basically allows you to trigger the events. I don't think we have the complete video, but we can look into that later. So this section talks about how to build an agile team, the agile team development framework for ML deployment. So basically, like I said earlier, there are different components involved in the workflow, and you have different engineers working on different things. So the whole goal is to build an agile team where you have people good at what they know how to do best, and they're using the best tools to do that. But at the end of the day, you want to couple all these things together and make it into a product that the end client really appreciates and understands. So in this case, this is kind of like how it looks if you want to build a collaborative team workflow, where different person is responsible for different components, and these components will change over time. So let's say we have the data reader component, and that component basically changes. You have more requirement for the customer, or you're supporting multiple customers, but you don't want to break the backward compatibility. The cool thing about this is like using Docker containers, you can create a tag and give it a tag. Like, okay, this is a version 1.0. If you have a new component, you have version 2.0, and you deploy, and those two containers that contains your code is to basically in your repository, the engineer and XML engineers can grab whatever versions they have based on the spec definition and build a pipeline. And the pipeline components you can change, like in this case, a data transform component. You can decide to like maybe extend the features you want to expose to the data scientist and stuff like that. So every time you can just point to the right one, publish a new component. And once you publish the component, the data scientist can pick it up. Okay, this data scientist still needs version 1. They can build their model based on version 1 of the data transform component that this ML engineer built. Or this ML data scientist needs more features, then you can basically extend what you have in version 1 and create version N, and this guy can build it. And the cool thing about it is like they can all be running their infrastructure and building their pipeline without worrying about what's going on and stuff like that. So basically, that's how you work in a collaborative environment. Each BIM job is containerized as a manageable unit. That's the whole point. You want to make sure you can containerize your work in any language you're using, R, Python, Java, Scala, Golang. You want to try to containerize it. These containers can be versioned and tracked with other artifacts needed for the model deployment. So you want to be able to know the version of the container you're running, and you want to know the version of the pipeline, the data point, the data set that you used, what version or what dates, and things like that. So you maintain all those artifacts, and it makes it easy to go back in case you're doing like an audit on your pipeline to know what happened, if something happened and stuff like that. You can know the kind of data you used, who delivered it, and the kind of the pipeline, the model, the git coming for the code version and stuff like that. So the pipeline for Argo Workflow 2 is the pipeline 2 is all in Argo, and it's also tracked in version. So it makes it easy to know what's going on, like I said, and the output artifacts that you basically produce as a version. So you have a version for the model, and you can always know what version of the model you're running and how you produce that model. So so the Argo component versioning, basically it's like this. Let's say this is a pipeline you're working on, and you have different people on the team working on different versions of it. So you can decide to like create a new version, you tag it, and that version can now be used to train your model and stuff like that. So you can have pipeline component version changing. So you want to be able to track that on your team. Or you can change the entire pipeline. So you might decide to like, okay, based on new set of requirements, basically create a new pipeline. So that's one of the advantages and creating a workload that you can easily track and version across infrastructure. So let's just like cap off all spoken a lot this month today. So if we go back to the earlier slides, these are the challenges that basically we pointed out: reproducibility, reusability, manageability, and automation. So those are the big challenges in the MLOps space and getting machine learning into production. That's why you still have people build models, but the models cannot scale and they cannot push it out, even though they look good and fancy on the Jupyter notebook, but getting it into production where people use it at scale is what really important. And once you do that, that's when you become the Googles, the Facebooks, and the Ubers of this world. So the challenges, like I said earlier, reproducibility, reusability, manageability, and automation. Those are the main key pain points. But in our case, using Argo workflow on Kubernetes, we've been able to like basically reproduce our pipelines. So once you create the pipelines that contains all these containers that runs in the workflow, you can easily reproduce it. That means I can give you my pipeline code and you can execute it. And the same thing I got, you should be able to get it if you run the pipeline the same way. So that solves reproducibility for us. Reusability, we were able to do that because once we containerize our applications inside a Docker container, we can easily hand it over or share within the team. So basically containerizing your application and containerizing your application makes it easy for you to like share with your teammates, so you can version track it like you saw earlier, and you can basically use that across all applications. And the BIM API, IOs and everything, we have different data reader components, you have data transform components and stuff like that, what we use in other projects. Then the other thing is the manageability. So managing your application means you want to be able to like basically control the life cycle, make sure nothing, like spending too much, your resource constraints and everything, you're able to manage it effectively. So with the issue of that, basically being portable across infrastructure makes it easy for us to manage the process. And you can easily deploy things on your local to test it out before moving it to the cloud. And we're not like married to one cloud infrastructure. We're basically agnostic, and you can shift and lift and deploy these things between infrastructures. And the final point is around the deployments and automation, which we basically leverage a lot of GitOps process. GitOps process is a way of you managing infrastructure deployments using Git. So you can basically version the entire resource that you're going to deploy on the cluster. And whenever there's a new version, you can take it out and deploy the new version or upgrade by just doing a Git commit and stuff like that. So lesson learned from plus summary: Apache BIM portable runner blueprint is very solid, even though it's still evolving. So we leverage it a lot right now, but it's still evolving. So things are going to change. A lot of the things I'm talking about right now may be invalid in the next few months or years as the specs changes and stuff like that. So you want to keep an eye on the documentation, even though it's very sparse, but there's a lot of things going on in that space, and it's something you want to look at. So it makes it easy for us to quickly test our implementations on a small scale. Basically, we can run the entire pipeline on a Minikube running on a local laptop. And once everything is ready, we can shift and lift and deploy it into the cluster. We're able to leverage BIM Kubernetes development environment to make it easy for our data scientists, ML engineers, and data science engineers to easily collaborate. So what that means is like we have different people play different roles in the entire ML lifecycle. You have data scientists, data engineers, ML engineers, DevOps, and everything. But one thing that is not consistent between all these actors, their environment, and the way they approach things. So one of the things we've done is to basically create a mono repo that allows everybody to pull the code from the same base, set up the environments, work on the code in the same way, and deploy the infrastructure. That way, there's a little to zero impedance mismatch between the local environments and what we have in the production environments on the clusters in the cloud or on-prem if the customer is on-prem. Then the version of the job SDK containers are easily changing because there are different components involved in this process. So one of the pain points for us is knowing what version of job service we're using and what version of cluster that supports. So if a job service supports version 3.0 of Spark and you're using version 2.0, then there's going to be an impedance mismatch because the specs are different between those environments, and you run into a lot of problems. So tracking that and making sure that you have all these things in the right place will basically help you in maintaining harmony between all the components, and everything will play nice with each other. So that's one thing you want to look at. Aside from the initial overhead, so all these things, there's always a price to pay. So with managed service, everything is in there for you. You can just go in and use it. But in the long run, your costs as your application size grows will become the curve for your cost goes up. But in this case, there's always the initial overhead of setting up the environment, bootstrapping the infrastructure, making sure everything is okay. So I think that's the initial cost that we pay for this. But once we ramp up all our engineers in the space on the old idea and everybody gets familiar with it, we notice that productivity and efficiency increased significantly. And cloud is not cheap. One of the challenges a lot of medium-sized to small startup faces the ramping cost of cloud infrastructure. Once your engineers start putting things on the cloud, it costs money, it's not free. So if you can bootstrap a local environment like this and get your work done and test it out before you push it to the cloud, it will save you a lot of money. So I think that's it. Thank you very much. I don't know if we did well with time, but we'll probably have like a few minutes for Q&A. If you have any questions, let me know, and I'll be glad to answer. Thank you.
Thank you very much, Mr. Charles.
Thank you.
So just before we take a couple of questions from the interns, I'd like to point out that the second attendance form will be dropping now, and the secret code is machines. It's all lowercase, machines. So please, it'll be available for just 10 minutes. Whatever platform you're watching this from, check it's pinned right now. So either YouTube or Zoom, and the code is machines. All right, and now to our questions. So we have, one of the questions that we have here is from David Quenel in the Zoom platform. Is asking, is Kubernetes a must-have skill for a fresher data scientist? Is it a must-have skill for data scientists?
Good question. I think it's a nice to have skill. It's not something you might want to go deep on, because like they're probably like people dedicated to managing Kubernetes infrastructure and stuff like that. But I think as a data scientist, you probably want to have a good knowledge of how it works, because it looks like that's the direction things are going right now. Every company building applications, they want to deploy it on Kubernetes. So I think understanding it from the user or operational perspective might be a good idea, but you're not going to be the one deploying the infrastructure. Well, you can grab a Minikube, and with few commands, you can run it. The documentations are solid. So it's something you might want to look at, especially if you want to see how this thing works from a user perspective. So you don't want to build a model and just hand over the notebook to somebody else to implement the deployment. So if you want to understand that and be involved in that, I think it's a good skill set to have.
Okay, thank you, sir. I hope that answers your question, David. So a lot of the interns are requesting for your slides, sir, as well as the codes you used for the demo. I don't know if they'll be available for them.
Yeah, good question. So we're gonna make the slide available after this call. The code will push it out. More people have asked for it as well from the conference, so we're gonna make it publicly available on there on our GitHub repo. So just be on the lookout. And if you have any questions, oh yeah, the email is up here. You can drop us a mail as well.
Okay.
Yeah.
Okay.
And if
so
you're beyond that, if you want to extend it and participate in some of our open source initiatives, you're welcome as well.
okay, thank you. We have another question here. In regards to Docker, someone wants you to expand a bit more on Docker and its place in all of this.
Yeah, sure. So before now, everybody building applications, they just build it up and push it to an entire server, or build it up and everything runs on your computer. But you can think about Docker as kind of like an application. So on your phone, you have different apps. So you don't just kind of like the way the phone was before that. The only thing you can do is to just maybe make a phone call, and the old phone is just for phone call, which it's not a productive way of. If you look at it application perspective, you want to run a web application, and you have entire computer being used as a web server. But the downside to that is like you're wasting resource. So one of the things that Kubernetes, like Docker solves, is like you can containerize your work, and once you containerize your work, you can easily package what you've done and deploy it in a different environment. So that way you have all your packages isolated and all packaged in one place, and it makes it easy for you to manage all your applications. So I think if you look at it, there's a spec for it. It's been around for a while, and everybody uses Docker right now. So you have Docker for Golang, for Java, for Python, and everything that you're doing and stuff like that.
Okay, thank you, sir. So another question, although not related to our topic today, I'm sure they could use your help. How much?
I think I lost your audio. Can you come again? Hello?
Algorithms is enough to learn to become a data scientist?
Can you repeat that question again for a second? I think you went off.
Okay, so the question is, how much data structures and algorithms is enough to learn to become a data scientist?
As much as possible. I don't think there's any limit to what you should learn or how much, but the more you know all these things, the better your code and quality of your work is. So initially, and one thing you see as you start doing all these things is if you evaluate yourself, you see the evolution over the years and over the period of time. So, I mean, the main thing is to just get started. And if you go back after 6 months and you look at your code, you'll be like, oh, did I write this? Man. And if you go back over the years and you see how your codes evolve and the way you do things, you always laugh at your codes and the way you got started because you evolve over time. So I won't want to say this is how much you need to know or not know. There's a lot to know, and the more you know, the more you discover you don't know. So the question is like, how much do you want to know? And it's all up to you. And I don't think there's a value of the size of what you need to know, because there's still a lot that I don't know myself, and I'm still trying to know. So try to know as much as possible.
Okay, thank you very much.
Yeah.
I think a hand is up. Orina, can you unmute yourself and ask your question? Orina, can you unmute yourself?
Oh, you can type it. I don't know.
Okay, sorry, just to ask a brief question. I just want to ask, which certification can someone in data engineering and MLOps opt for?
I mean, there's a lot of certifications out there. although I'm not a fan of certification, but some people like to do it to evaluate themselves. But I mean, the different certifications around Kubernetes, Google Cloud, Amazon, Azure. But if I think just spend a lot more time to understand all these things, because I mean, certifications tells you that you know this and that, which is good, but there's always a big difference between someone working with it actively every day than someone who just got certified to get a job. So one thing I will encourage you to do is to all these projects and all these things that I'm talking about, they're open source projects. Join the open source community, read up the documentations, go through the code base, ask questions, review pull requests, contribute. I think you learn a lot more better and faster that way than getting certified in a particular stack or technology. Technology will always change, so certification will always become obsolete, but the knowledge you acquire and the basic principles and fundamentals, they're always going to stay with you. Any questions?
Thank you very much. In the absence of any other questions, I'd like to say that we've officially come to the end of today's webinar. And I want to thank Charles Adetiloye for taking the time to educate us today. I think, I was about to round up. I think we have another question. We'll take this. This is the last one. So, James, can you go ahead and ask your question?
Just a quick one, please, Mr. Adetiloye, I want to ask, is the Kubernetes like a Jupyter notebook that we have to download to use? Or is it just, how do we use the Kubernetes? Is it an app or is it a notebook, something that we could use? And also the Argo workflow, is it also an app or like a Jupyter notebook that you have to use, you have your codes and the rest of them on the Argo workflow?
Good question. So I'll share my screen back real quick if I think I'm still sharing. So I'll just point you to the website. I should have actually done that. I assumed a lot of things going into this. So this is the Argo project. If you go to argoproj.github, it contains all the things you need to learn about it. They have the code base. You want to check it out, so just go in and view. They have the project is very active. People are always committing. Someone just committed 2 hours ago, and something that you might want to take a look at. They talk about workflows and how you build a workflow. Check out this video. They went into details more than I could do, and the Kubernetes. It's another big project. They have the kits if you go to kubernetes.io. So they have a lot of documentation around it. So just check it out. There are a lot of videos on YouTube and stuff like that. So just check it out. It's basically kind of like you download it and you install it, then you can start touching all these applications and everything around it. So just go ahead and check the documentations out. And if you have any questions, you can just drop us a mail. Somebody will reply to you and point you in the right direction on that.
Okay, thank you, sir. Yes, David, please go ahead with your question. David, can you unmute yourself and ask your question?
Okay, thank you very much. I just want to point you to the YouTube chat box. There is a particular question there that I'm missing now. Somebody is asking, how is Kubernetes applicable to data storytelling? I think it's a very nice question not to miss out. Thank you.
Oh, yeah, sure. Thank you. Yeah, so basically data storytelling is around visualizing your data. So eventually you can build your application and build a microservice that runs on Kubernetes. Kubernetes, not Kubernetes, Kubernetes. So you basically can build your application that runs on as a microservice, as a service or an application that runs and you can deploy on Kubernetes. So that's one way you can publish your content and push it out to Kubernetes, your blog, your and all these things, contents, website, and everything can all be deployed on Kubernetes as well. So you might want to look into that. And I think it's going to be part of what we focus on heavily in the next cohort of trainings at Amoye. So you might want to look into that as well. Any other questions?
Okay, so I don't think there are any other questions. Please, if you have any other questions, we'll take it now.
Yeah.
Okay, in the absence of any other questions, so I want to thank you, our dear interns, as well as our visitors for joining us today. I also want to thank our guests for taking the time out to educate us today. And I'm sure we've all gained some very valuable insights and knowledge. And so Amoye is saying a big thank you to you for joining us today. And we're also saying a big thank you to the Amoye team and everyone who saw to the success of this webinar. Until next time, do have a lovely weekend. Be rest assured that the slides will be made available to you. And of course, if you still do have any questions, you can always reach us on our Slack channels and via mail. Thank you very much and do have a lovely weekend.